Okay, good morning, ladies and gentlemen. Here, I am standing here maybe. Check. Check. Iya. Oh, ini dimatikan nggak apa-apa. Online, online. Oh, oh nggak online. Oh, oke. Oke, check, check. Okay, is it good? Okay, good morning, ladies and gentlemen. And the Honorable is Mr. Juan, Dr. Juan Paulo, and also Dr. Ahmad and Miss Ari. Uh, I'm standing here, Mayumi Puspita, as a master of ceremony. So today, it will a great opportunity to standing here together, learn with Dr. Juan Paulo. And yeah, Assalamualaikum warahmatullahi wabarakatuh. Okay, um, it's a wonderful and precision chance for me to be a master ceremonial today in this section to meet and learn with Dr. Juan Paulo from Division of Material Science, Nara Institute of Science and Technology. And yeah, we know that today we are discussing about the amorphous oxide semiconductor and hybrid material or sustainable flexible electronic. Okay, first, let all to us pray and praise to God because bless and mercy, we can come together with the healthy condition and yeah, meet with the guest lecturer today, Dr. Juan Paulo. Okay, ladies and gentlemen, um, on this nice occasion, so let me deliver the structure of the event of the today is the opening and then sharing session and also question and answer session and the closing. Okay, for the question and answer session, we have a several souvenir for askers. So for those who have a question, please we welcome about your question. We open about your question. Okay, so the next today the moderator is Miss Ari. The times I give you.
Okay, thank you. Thank you very much, Mbak Mayumi. Today I will moderator for Dr. Juan Paulo. Maybe before his presentation, I will read a brief of his biography. Dr. Juan Paulo is an assistant professor in Nara Institute of Science and Technology. He has a background in both physics in bachelor and master student in Ateneo de Manila University, and he finished his PhD in Nara Institute of Science and Technology in 2015. Actually, he is my junior because I finished my PhD in 2013. His work is on multidisciplinary research topic, including oxide semiconductor, hybrid material, thin films, electronic device physics, device simulation, and machine learning. a bulk of his research is performed with both academic and industry collaborator. He also served as program committee member in key scientific conference and reviewer for several journals. He is also have a research contribution and recognized with several awards, including EMFPD, ECS Japan Section Young Researcher Awards, NAIST Academic Awards, and numerous conference paper and presentation awards. Maybe today he will talk about maybe semiconductor, thin films, and maybe how is do the fabrication easier maybe in room temperature maybe Sensei. Yeah. Okay, maybe I give your time please, Sensei.
So thank you very much for the very kind introduction. And before I begin, I want to thank everyone for coming here. And I also want to thank UGM for giving us the opportunity to present our research and also introduce NARA Institute of Science and Technology to UGM. And I'm also very grateful for the great hospitality that was shown to us. So I'm very, very thankful. Actually, it's my first time in Indonesia. So I have a very wonderful experience in Indonesia and I can't wait to visit again. So actually in this talk, there are two parts. In the first part, I'll be talking about introducing our division, the Division of Material Science, and especially the NARA Institute of Science and Technology. And in the latter part of my talk, I will be introducing my research on oxide semiconductors and hybrid materials for flexible electronics. Unfortunately, the time is not so long, so maybe I'll skip part of the hybrid materials part and we'll focus on the solution process oxide semiconductors. So let me first introduce the Division of Material Science and NARA Institute of Science and Technology. It was working a while ago. Okay, now it's working. So NAIST is located in Nara Prefecture. So if you're not familiar with the geography of Japan, so Nara is in the middle of both Osaka and Kyoto, and NAIST is here between these three major cities. So you can, if you join NAIST, you can enjoy sightseeing in both Osaka and Kyoto. So our campus is quite compact. So we only have, our school is only just composed of graduate schools. So it's unlike UGM, which is very large and with undergraduate students, but in NAIST, it's only graduate students. So my building is here in the Material Science Complex. And currently we only have 290 master's and PhD students and 59 international students from 14 countries. So before, NAIST is composed of three graduate schools, so information science, material science, and biological science. It's quite a new university. It was only founded in 1991. So a few years ago, we underwent an organizational transformation. We combined the three graduate schools to form a single graduate school, the Graduate School of Science and Technology. And through this combination, we're able to offer 5 educational programs in information science, biological science, material science and engineering, and in the combinations like data science, digital green innovation. So NAIST is one of the top national universities in Japan, even if it's just very young. So it's only one of 2 universities rated excellent in both research and education. So the other university is Tokyo University of the Arts, and NAIST is got an excellent score in both research and education, and I think that's very. So in the Division of Material Science, we have so many labs, and each lab has its own different topic. So if you're interested in a specific topic, I'm sure that you're able to find a specific lab that will meet your research interest. So for example, some of the labs are working on molecular crystals. Some labs are manipulating surface atoms and electrons. And some labs are using machine learning in order to predict material properties and predict or optimize fabrication parameters and etc. Some labs are also working on transparent or flexible thin film transistors. I belong to that lab. And some labs are working on thermoelectric materials and so on. So there are many topics, and later I'll introduce some of the topics for each laboratory. So these are the research units in the Division of Material Science. So the division can be subdivided into 5 subgroups in physics, chemistry, device, biomaterials, and recently data science. So now we're also focusing on using machine learning and data science in order to drive innovations in material science and physics and chemistry research. So these are just some of the recent topics from the physics lab. So a lab was working on single cell manipulation using femtosecond lasers and elucidating the origin of material properties using holography. So this technique is very useful because, for example, at the interface, it's very hard to image these very small or tiny dimensions. So using holography, you can image these interfaces and study the mechanisms at these very small, very tiny dimensions. Another lab is developing organic semiconductors for lacing systems, so organic lasers. So these are the topics from chemistry laboratory. So one lab is developing molecular electronic materials using organic synthesis. Another lab is working on super photosensitive molecular materials. So these materials are very important because, for example, in your CPU, the channel lengths are already reaching like 3 nanometer level. And in order to pattern these devices, you need photosensitive materials in order to facilitate this patterning. So this development is very useful. And one lab is working on technomimetic or biomimetic functional molecules. So this molecule is actually a car. So if you stimulate it with using an STM, these portions of the molecule will rotate. And actually there's I'm not sure if it's every year or every 2 years, there's a race where every universities from all around the world develop their own molecules and race their nanopolymers or nanocars. So these are the recent topics from Device Lab. So I belong to this laboratory. So I'll discuss more of this topic today, so I'll skip it. So one lab is also developing thermoelectric materials. So as you know, your body releases a lot of heat. Also, your devices also release a lot of heat. So what if we're able to use that wasted energy in order to convert them to electricity? So for example, if you just put the thermoelectric powered device on your skin, the waste heat from your body will be able to power these wearable electronics. So another lab is working on developing very tiny microelectronic devices in order to implant on the mouse brain to study brain functions. So hopefully we can study how specific areas of the brain function and etc. So another lab is developing new materials and materials physics for radiation measurement, so scintillators. And these are from biomaterial laboratory. So some labs are working on biodegradable polymers, and some labs are working on protein and bio supramolecules. And another lab is, for example, working on creating artificial creation of natural spider silk. So materials with very high mechanical properties. So these are just some of the top in these laboratories. And the new labs, they're working on material science and deep learning. So for example, material science is machine learning is very useful because, for example, we can use it to predict experimental data or predict material properties. So I'll present actually some of that process in my talk later. So using machine learning to design molecules and monitor chemical plants, and also use machine learning in order to make analysis of, for example, your spectroscopy measurements to be more high throughput, and using multimodal analysis of the data. So combining images of the experiment and together with the with the experimental data and other relevant data. So the research environment in NAIST is quite, it's very good, not quite good, very good. So for example, we have transmission electron microscopes, XPS, X-ray photoelectron spectroscopy, and time of flight mass spectrometers, XRD, and so many other equipment that we didn't list here. So our research environment also includes the clean room. So actually I fabricate most of my devices in the clean room. So these clean room are class 100 to class 1000 to 10,000. So that means that there are only you can count the number of particles with a certain size. So class 100 means that only 100 particles can be found in that space. So it's very clean, cleaner than your surgery room. So we have many deposition systems, like sputtering systems, or atomic layer deposition system, and E-beam lithography, and also many other deposition systems. We deposit not only semiconductors, we deposit both conductors, semiconductors, and insulators. So in the Division of Material Science, we have also international faculty from France, China, Philippines, Australia, Thailand, and India. And in the international students are quite many in the Division of Material Science. So during my time, it was not much, but now it's many. So around 20% of the population of the Division of Material Science are international students. So some labs, the language used is English mostly. So it depends on the lab, but most Japanese also can speak English. So communication is not a problem usually. So these are some of the internship students that joined from Indonesia. So we're very thankful that UGM sends a lot of interns to NAIST. And these are the graduates from Indonesia. So maybe you will recognize some names here. So I think Diki Purnawati is from UGM, so she is my student. So these are the current graduate students from Indonesia. So again, many from UGM. So we hope to welcome more students from UGM in the future. So now let me proceed to my second part of my talk. So I'll introduce the laboratory I belong to and my research topic as well. So this is the Information Device Science Laboratory. So this is the picture taken during the graduation of the master students. So in the lab, we have many staff. So we have Uraoka Sensei, he is the professor, the head, and 2 assistant professors, and 1 specially appointed professor, and 2 visiting associate professors, and researchers, and the secretary, and some advisor. So the lab is quite big, so I'm not sure if this is still current. So around 23 students, and for the PhD, almost 9. So most of them are international students. So you can imagine the language in our laboratory is mostly English. So 11 master students and 2 are international students. So in our lab, we're to tackle the problems in developing sustainable society. So we aim to develop innovative electronics for a sustainable society in order to address food security problems, environmental issues. And we do that by developing devices for energy electronics and using high performance, low power thin film device technology. So the philosophy in our lab is that we combine, or we aim to strike a balance between devices and applications and basic materials and fundamental research. So we study fundamental research on semiconductors, biological supramolecular, molecular and diamond, and devices applications that can be applied on displays, solar cells, VLSI, memory, power devices, and sensor devices. So these are just a snapshot of the laboratory topics that we discuss or we tackle in the lab. So I will talk about this today. And here we're also developing thin film materials to reduce the power consumption. So for example, in the back end of line applications, so you can develop vertical transistors with very little channel lengths with low power, and also power devices using gallium nitride, and power generation using waste heat, so thermoelectric materials, and using photovoltaic devices, especially perovskite. So actually we have a collaboration with École Polytechnique in France. So we're researching on developing perovskite materials using sputtering. So it's opposite. So mostly perovskite research is done using solution process. But in order for it to be used for commercial applications, because perovskite is very unstable and very difficult to process using to apply to commercial industry if it's used by solution process. So we aim to develop perovskite materials using sputtering. So these are also some of the machine learning topics that we do in the lab. So we use Bayesian optimization in order to optimize the fabrication parameters. If you've worked in a device fabrication field, you can imagine that there are so many parameters that you need to change in order to, for example, deposit a particular film. So if you're going to do that experimentally, you will be wasting a lot of time and wasting materials in order to optimize the fabrication parameters. So using Bayesian optimization, we're able to optimize the fabrication process at a fraction of the time and the material cost. And we have successfully optimized, for example, the interface between the SiO2 and gallium nitride using Bayesian optimization. We're also doing natural language processing to build process data sets. So for example, you have so many papers in the literature, right? So what if you want to get the process conditions of each of those papers? If you have to do it manually, if you have hundreds or thousands of papers, you'll waste a lot of time. So by using natural language processing and machine learning, we can identify the key phrases, and we can identify also the relationships between these phrases, and we can extract the relevant information from these papers and build the database so that you can see what other researchers are doing in fabricating their films, for example. And also using image or deep learning in order to evaluate the reliability of solar cells. So we use imaging to predict like the cracks in the solar cell. And I'll discuss this today. So we use machine learning level of the materials. So let me proceed to my talk. I'm sorry it's quite long, but if you imagine the evolution of devices, so one can only look at the phone, which is one of the most important devices that we have now. So before, this is not during my time, so I'm not that old. So, yeah. So during that time, the devices were very large and bulky, and only a few people actually have this device. And as we age, my time is around here. So you can see that the phones became smaller, and now we have even foldable or flexible phones. So what is the future? So we don't know yet. But if you look at the evolution of the mobile phone, you can see that one distinct part of the phone became very large, which is the display. This is because the display, we don't really use it to view information. We also use the display to interact with our device, right? So you use the touch screen in order to interact with your display. So in the future, we don't know what kind of display will there be in the future. So in the near future, I think it will be AR and VR related. Maybe in the future, it will be light field or holographic related. So actually, there are already some prototypes, and I have seen prototypes of holographic displays and light field displays. They're amazing. So in the display device, there are so many pixels, and these pixels are controlled by your thin film transistor. So they control how your individual pixels turn on and turn off. So if you're not familiar with thin film transistors, I will explain. So this device has three major parts: a conductor, which is the source, drain, and gate; this one, and then insulator, the gate insulator, and then a semiconductor channel. So the idea is that for the thin film transistor, I'm simplifying here, but this is an oversimplification. So if you apply a gate voltage higher than a threshold voltage, there will be current across the interface between the channel and the gate insulator, across the source and drain. And if you don't apply a voltage, or if the voltage is lower than the threshold voltage, there will be no current. So basically, it's like your light switch. So you turn on, there's current. You turn off, there's no current. So that's the basic idea behind the thin film transistor. So, but in the thin film transistor, this part, there are 3 channel materials that you can use. So amorphous silicon, this is the de facto or the standard channel material that was used before. This is because it's amorphous. As you know, amorphous means that you can extend it to a very large area. So the very old TVs, the very large area displays that was used before, use the amorphous silicon. But for your smartphones now, you're okay with the polycrystalline silicon because you want the mobility to be as high as possible. So that means higher refresh rate, and because the mobility also controls the brightness of your display, you also want high mobility. But the problem is that it's polycrystalline, so it's not uniform. So the development of amorphous oxide semiconductor was a wonderful thing. So it combined both the properties of amorphous silicon and polycrystalline silicon. It has a mobility of between 10 to 100, and since it's amorphous, it's very uniform. So let me explain this plot. So maybe it's not familiar for everyone. So basically, this is we call it the transfer characteristics. So you have 2 parts here, the on current here and the off current here. So basically, we want the on current to be as high as possible, and we want the off current to be as low as possible. This is because if you think about it, if your display is off or your device is off, it's actually not, so it's expending a lot of leakage current. So if that leakage current is high, and if you have so many pixels, you're wasting a lot of energy or battery. So that's why old phones before have a very poor battery life. So now most devices use amorphous oxide semiconductors or the evolution of this amorphous oxide semiconductor. Now, to get to the fundamental part, why is it that when we move from amorphous silicon to polycrystalline silicon, there's a large drop in the mobility? This is because for the silicon, the electron transport is controlled by these sp3 orbitals. So you can see that these are highly oriented. So if it's amorphous, it's randomly oriented. So your electrons can no longer transport quite well as compared to the amorphous oxide semiconductor. The conduction band is mainly formed using these very large metal NS orbitals. So these orbitals are very large. So even if there are some misorientation, for example, in amorphous, the electron can still pass through the very large overlaps of the s orbitals. This is why the amorphous oxide semiconductor still has a high mobility, even if it's amorphous. So these are just some of the requirements for the display. So in the future, if you want to use AR or VR goggles, you need mobilities of around 100. Because, for example, if you want to use super high vision, this is very high, high frequency and high pixel density. So you need these very high mobilities. So this is just showing the development of the amorphous oxide semiconductor. So it was discovered by Professor Hosono's group in 2004, and then after it was commercialized. So without the development of amorphous oxide semiconductor, you will not enjoy the OLED or your Apple Watch. So the always-on display in the Apple Watch is using the combination of LTPS, or low temperature polycrystalline silicon, and oxide semiconductor. That's why this device is always on, because the oxide semiconductor uh, power consumption is very low. So this is just the previous slide, but these are the applications of amorphous oxide semiconductors. But amorphous oxide semiconductors are not only used for display. They are also used for memory, for neuromorphic computing. So for example, in mimicking how your brain operates. So the traditional way to compute is separate. So you have computation in your CPU, and then some of the data is transferred in the memory. But now we want to develop neuromorphic computing. So in this case, computing can be done in memory. So computing in memory. So that's due to the advances in neuromorphic computing. And it can also be used for sensor applications, light sensors, gas sensors, pressure sensors. And we can do that by modifying specific areas or specific layers of the transistor, the channel, gate insulator, and the device structure. So additional functionalities can be unlocked through various TFT modifications. But now, we want to aim towards a new paradigm shift. So this is how we fabricate most of these devices. In the lab scale, you have oxide spotter, PECVD, ALD, PLD, and etc. And in the lab scale, to move to industrial scale, you basically just blow up these equipment. So very large ALD, very large PECVD, very large sputtering. But in order to develop many devices in the next generation society, where you need many sensors, many neuromorphic devices and devices for machine learning and data processing locally, we want to develop a high throughput fabrication, similar to how we fabricate newspapers today. So it's purely solution process. So all layers are fabricated using solution process. So this is just what I said earlier. So I think amorphous oxide semiconductors can address these requirements. And using solution process is quite good because it's simple. We can form diverse structures. It can be used at low temperature. It's cost effective, and it can be scaled to a large area. And it we think applications in fitness, medical, and communication and fashion. And these are the current trends in solution process. So before, there were not so many papers using solution process, but it's steadily growing. And most applications or most research have been done in order to improve the performance of the solution process. So for example, we design or engineer precursors or solution material. Several methods in order to improve the performance, like photochemical activation, annealing methods, and combustion chemistry. But the problem is, most of these research are only focused on a single layer. So if you want to do this, all layers should be fabricated by solution process, not only the channel or the semiconductor layer. So our group has been hard at work doing that. So each of these layers, from vacuum process in blue to green, using solution process. So due to lack of time, I'll just focus on two areas, the channel and the source drain region or the conductor region. And the challenge, of course, is when you from vacuum to solution process, there's a dramatic reduction in performance and especially stability. So that's why it's not used for industrial applications right now. So we want to work on this. So now let's proceed to the channel. So for developing solution process channel semiconductors or oxide semiconductors, the type of precursor is very important. So for example, you can start with, before they used chloride precursors. But as you can see here, this is a TG-DTA, only TG measurement. So you can see here the weight loss occurs at around 350 degrees Celsius. So you need very high temperatures in order to remove the unwanted impurities. But if you use nitrate precursors, the temperature needed is only around 200 degrees Celsius. So in our lab, we also developed several processes in order to uh, fabricate these solution processed films. So for example, if you want to fabricate your devices on PI, PEEK, PEN, or PET, or even paper, or anywhere, you need to lower the process temperatures. So in order to do that, several groups have developed their own processes, so using hydrolysis, combustion processing, or steam annealing. In our lab, we developed wet O2 annealing and using UV laser annealing. So I'll discuss this later. So next is the source drain. So remember, our goal is to make each of these layers a solution process. So these are the plot of the available transparent conductors. So y-axis is the conductivity, x-axis is the cost. So as you know, graphene can be a conductor, a very good conductor in fact, but it's very expensive. And this is the figure of merit. When I say figure of merit, it's the transparency divided by the sheet resistance. So you want the figure of merit to be as high as possible, and you want your process temperature to be as low as possible. So you want to be here. So these are the minimum requirements for display, touchscreen, and photovoltaic applications. So in effect, we want to develop materials that targets these areas. So quite cheap and high conductivity, high figure of merit, and low process temperature. So previous methods have been used to transform oxide semiconductors into conductors. So you can use reactive aluminum treatment. So you basically diffuse aluminum into the semiconductor to transform it into a conductor. Reduction via metallic calcium, HN argon plasma treatment, and photochemical hydrogen doping. But the issue is that these temperatures are quite high, and it's a lengthy process, up to 4 hours. So in my lab, we developed a method that is rapid. So we use a RF excimer laser in order to transform the semiconductor into a conductor. So by irradiating the semiconductor by a single shot of the excimer laser, we can transform the semiconductor into conductor using a very rapid time. So only 9 nanoseconds is the pulse width. So very quick. So we show here that without irradiation, the sheet resistance, which is related to the conductivity, is very high. And as we irradiate or increase the fluence of the laser, and we perform it in vacuum or in argon, the sheet resistance is dramatically reduced. And even if we perform the laser treatment, the films are still transparent. So the laser does not change the opacity or the band gap of the semiconductor. So this is the other studies on transparent semiconductors, and our study is quite here. So very high figure of merit and very low process temperature, because the laser, it only the laser is only selective at the surface. The substrate region is not does not experience temperatures. So as I said before, most solution process studies use a single layer. So we want to develop all solution process for the TFT. So these are some of the all solution process TFTs that is in the literature. So very few. And most use complicated fabrication and diverse materials. So using carbon nanotubes, nanowires, and ruthenium oxide, and P.PSS, and nanowires. And the mobility is quite low. And remember, I told you the mobility should be 10. And the substrate temperature is quite high, so it's not applicable for flexible applications. So in our group, we developed this method, so the all solution process TFT. So we spin coat the oxide semiconductor. We use indium zinc oxide. We spin coat the siloxane. This is the gate insulator. And then another layer of the semiconductor. So this is the top view of the device. Of course, semiconductor is a TFT because conductive electrodes, right? But after you irradiate it with UV, you selectively to a conductor. So in effect, a single layer is both a semiconductor and a conductor. And then you get the switching characteristics. And if you do ELA after this, or excimer laser annealing, you get mobilities of up to 25 square centimeters per volt second. And we also have further improved this process, so we can get mobilities of up to 40 square centimeters per volt seconds, which is fully solution or solution process TFT. Remember that the all solution process TFTs before, the mobility is quite low, only 10 square centimeters per volt seconds. And this is just some of the characterization. So what happens is that this is the as deposited film. It's amorphous. After UV, it's still amorphous, and after excimer laser annealing, it's crystalline. So this is the TEM and the corresponding SAED diffraction pattern. So you can see that maybe it's not clear here, but you can see the moire patterns, and these signify that the gate and source drain regions are crystallized after the excimer laser annealing. So this is the mechanism. So what happens is that as deposited IZO is semiconducting, so there's no sufficient conductivity. And after you irradiate with UV, we found that the energy from the UV light ejects some of the oxygen in order to form these oxygen vacancies. And it's well known for in the oxide semiconductor field that as we increase the amount of oxygen vacancy, more electrons or the carrier concentration is increased. So that's why the conductivity is improved. So with the crystallization by the excimer laser annealing, you also enhance the charge transport of these carriers. So this is just a COMSOL simulation showing the temperature during the laser treatment. The red means high temperature, so this is 1,600 Kelvin, so very high temperatures. But if you notice the blue part, so this blue part is the substrate, so it still remains at almost room temperature or below 50 degrees Celsius. So I have a temperature here, so it's less than 100 degrees Celsius. It means that we can use any substrate using this process. And we did that, so we fabricated all solution process TFT on the flexible polyimide substrate. So it's flexible, and using the UV only or UV laser, we can still get switching characteristics. So this is just the benchmark. So these are the old all solution process TFTs before, and this is our work. So very high mobility, and maximum temperature in the substrate is only 300. This is due to the deposition of the film. We need around 300 degrees to form the oxide. So now we can develop devices using a roll-to-roll fabrication, similar to how we make the newspaper. So in effect, this flexible substrate just keeps going on, and then you deposit the AOS or the oxide semiconductor, the insulator, and then another layer, and then you selectively change them to conductors using the photonic process or UV and ELA. So what are the future prospects? So there is still a lot of work to be done. So for example, we can change the gate insulator to high K material or ferroelectric material to get neuromorphic computing. We can also change the electrode region. We can also use combustion processing or alternative oxide semiconductor using P-type or ultra-wide bandgap material, and using machine learning. So today I'll discuss the alternative conductivity enhancement method and using ultra-wide bandgap material. So both of these studies are done by Indonesian students under my supervision. So Hanifa is from University of Indonesia, so she will graduate this September. So she studied alternative post-process treatments for the the all-solution process TFT. This is because I didn't show you the stability, but if you only use UV, the transfer characteristics are not stable. When I mean by stable, when we apply the stress on the device, the measurement should be the same, so it should be overlapping. So this is after 10,000 seconds. So you can see there's some shift. So we want to develop a new method. So in her case, we used plasma, argon plasma. So as before, the as fabricated is not switching because there are no conductors. And by using argon plasma, you can selectively convert to conductors. And then you can get very good switching, up to 30 square centimeters per volt seconds. And the PBS is also improved. So as you can see here, when we apply positive voltage for up to 10,000 seconds or more than 3 hours, it doesn't change much. But we are still hard at work to improve the negative bias stress. So this stress is when we apply a negative voltage. So there's still more work that needs to be done. So we found, I think I will skip this because there's, okay. So in the XPS analysis, we found that this is the O1S spectra. So there's a shoulder peak here. So this signifies the formation of oxygen vacancies or other impurities after the argon plasma treatment. So what's special with the argon plasma treatment is that it doesn't crystallize the amorphous oxide semiconductor, so it's still amorphous. The sharp peak here is not from the semiconductor, it's from the silicon substrate. And we found that by irradiating or by using argon plasma, the film density is increased from 4 to around 6. If you notice, the density of solution processed films is very small. So this is actually a problem of solution processed films. So typical vacuum processed films will have densities of around 6 grams per cubic centimeters. And during argon plasma treatment, it's still smooth because it's still less than 1 nanometer, the root mean square roughness. Of course, it will increase because of if you do argon plasma, there's ion bombardment. So the high energy ions bombard the surface of your semiconductor. So of course, the roughness will increase, but only slightly. So it's still transparent. And this is the mechanism. So we think that the ion bombardment during the plasma decompose the weak chemical bonds, forming the oxygen vacancy. So this is the schematic. And also, the plasma-induced film dentification occurred after the plasma treatment. So there's a noticeable increase in the density of the film after the plasma treatment. So we also show that it's possible to do for flexible substrates. So this is fully solution processed transistors on flexible substrates after argon plasma. So next, I want to talk about this topic. So previously, I showed you examples of amorphous oxide semiconductors using wide bandgap semiconductors. But in the future, I think ultra-wide bandgap semiconductors will be useful. This is because they have high breakdown voltage, they have excellent optical quality because of the very large bandgap, and they can be used for many applications. So for example, for harsh environment or harsh environment resistant applications. So for example, in space or in very harsh environments. So they can be used for solar blind photodetectors, sensors, and TFTs. Now the problem is, of course, if you have a very large bandgap, normally you will think that it will be an insulator, right? So how do we transform that into a semiconductor? So Diki from UGM, so she used hydrogen annealing to convert the insulating amorphous gallium oxide ultra-wide bandgap semiconductor into a semiconductor using the hydrogen annealing. So what happens is that if you anneal the semiconductor in hydrogen, the Fermi level will be shifted closer to the conduction band due to the additional states introduced by the hydrogen. In effect, the insulator is transformed into a semiconductor. So we call it Fermi level engineering. And to do Fermi level engineering, we had to do many experiments like vary the film thickness, vary the baking temperature, vary the annealing gases ambient, and etc. So by varying these experimental parameters, you can tune both the band gap and the Fermi level. But as you know, it's very expensive experimentally and time-wise. So you can predict the Fermi level using experiment. So you make the sample and then measure using a combination of XPS and UV-Vis or ellipsometry. You can also do simulation. So for example, for simulation, you can do DFT. But DFT for amorphous is very challenging or impossible. So another method will be machine learning. So we train the machine via the experimental input from various input data. So from literature or from experimental data. So this is the experiment. So we synthesize the precursor, and then we prepare the substrate, deposited the film, and varied the thickness, baking temperature, and the gases, the concentration, and the annealing temperature, and then we measure the EF. And we fed the experimental data to this system. So this is because when you change, for example, specific parameters of the semiconductor film, the thickness changes the properties. So for example, when the thickness is increased, the band gap also decreases and the Fermi level also decreases. So it becomes more conductive. So, but if you have so many parameters like thickness, annealing, H2 percentage, and temperature dependence, it's very hard to show the exact relationships between these parameters. So the Fermi level has a complex relationship with the experimental parameters and the band gap. So at first, to do this experiment, we pre-processed the data. So we fabricated samples, and these are the corresponding EF and the corresponding process parameters. And we performed Pearson correlation. So the correlation was quite good. So we can use these parameters. And then we separated the data to 25% testing and 75% training. So the training data is fed 75% to 3 regression algorithms. And then we performed machine learning ML validation. We used leave one out cross validation to optimize the hyperparameters. And then we performed the testing to test the model. And we found that using the using the random forest regression, we're able to get an accurate prediction of around 87% with an error of the Fermi level of plus minus 0.09 EV. This seems small, but actually it's still quite big. Plus minus almost 0.1 EV is still large, but it's a large improvement over previous methods. And we can predict with 87% accuracy. So I'll skip that. And because of this, because of the model, we can predict the Fermi level in a wider experimental range. So we don't have to do these experiments in order to get the Fermi level data. So the machine learning has predicted what will be the Fermi level if we have a specific thickness, a specific baking temperature, and a specific hydrogen percentage. So for example, if we have a thickness of 90 nanometers, a baking temperature of 425 degrees Celsius, or an H2% during the annealing of 4%, you'll get a Fermi level of 1.38 EV. And we also tested, of course, if it's true, because if it's not tested, then how can you know it's true? So we actually performed the real experiment, and we get 1.4 EV, which is very close to the predicted machine learning data. So this is very useful in the future. So I hope that more students are interested in machine learning or data science. So this is just the summary. And the previous work and this work, they predicted the band gap, not the Fermi level. But you can see the accuracy is only 8%. The error is very large, 1.73. But in our study, it's very low. So 0.1 almost, and 87% accuracy. So hopefully, this is the end of my slide. So hopefully I'm able to show you how solution process thin films can be used for flexible electronics and how data science can be used to fabricate these thin films. So we think that using this technology, you can have low temperature and high performance, and it has a mass production potential. So of course, I want to thank several collaborators in Kyushu University, TU Delft, Merck, and Nissan Chemical Corporation, and the funding agencies. And I especially want to thank students in my group. So not all of these students are my students, so just some. So majority of the research I presented here were done by students from Indonesia. So Dr. Hanifa and Dr. Purnawati. So if you're interested in joining NAIST, so actually there's a NAIST DMS study abroad. So I think this was already shared to your supervisors, I think. So it will be on September 7. So there will be an introduction of NAIST and the life in NAIST, and information session on how to join, on the introduction of several laboratories by NAIST faculty members. So you can join using this link. And for more information, you can ask the office. So finally, this is the end. Thank you very much for your attention. I'm sorry it's quite long.
Thank you very much, Sensei, for the nice presentations. Now is a question session. Please, the student, if you want to ask. There is a souvenir from Ina alumni. So you can ask anything about the topic or about NAIST program. So the last slides shared by Bermuda Sensei was a studio board fair from the DMS, from the material science. So I already get the email from Maki-san's yesterday.
Okay.
Just yesterday. Nice. So I will not yet share to the students. So maybe later.
Yeah,
That's include the internship program. Usually we send the student to NAIST for internship, and the good news is this year the internship will be on site.
I think.
So maybe online and on site. So maybe there's a chance for you, for the master student, to do internship directly to NAIST.
Yeah, to the lab. Yeah.
Okay. Please, there is a question maybe.
Yeah, even simple question is okay.
Oh, Mbak Mayumi will asking. Okay.
Yeah.
Okay. Check. Okay, it's a good presentation, Mr. John Paulo. So I have a question that it's make me very interested about the machine learning. So also I'm studying about machine learning, but my major is sensor. So I use a data sensor for input to machine learning, to classifying, and to prediction. Yeah. So in here, is it not in the optimization about the Fermi level. So actually there is have the some point of we input that for I need to know about what is the component when we input, or what is the what is the data when we input the machine learning. Yes. So it's make me like when I study about the sensor, so the input is the response of the sensor, right? So that is the millivolt and etc. So how about the preprocessing in the Fermi level, and how we can find about Fermi level to input not only Fermi level, right? So that's how we know about the temperature and also the thickness of the material, and we it's like, what is it? It's like some the table of the material, so the big table, and we can combine any material, right? I don't know. I want to ask you.
Okay.
Yeah.
That's a nice question.
Yeah.
So actually here, we only focused on one material, so gallium oxide. But the question about the input parameters is quite good. So in our case, for example, in fabricating this film, you have so many parameters
Right.
like thickness, spin coating speed, but I didn't show here, temperature, the type of gas, and the time itself. But in order to cut down on these so many parameters, you can perform a Pearson correlation in order to find which descriptors or which parameters are relevant to predicting the Fermi level. So in this case, the input are these: the thickness, temperature, the gas type, the gas concentration, and also the temperature during annealing, temperature during baking. And we cut down on these parameters using Pearson correlation. So we only focus on the input parameters that have a high correlation with each other. So here the output is the Fermi level. In your second part of the question, I think you asked how do we know about the
Yeah.
temperature?
Yeah.
So and the thickness. So you still have to do experiments. So you need to do experiments to determine the thickness. You still need experiments to do to determine the Fermi level. So, but instead of performing these experiments 1,000 times, you only need to do it like 30 or 40 or 50. Or, of course, as you perform more experiments, the model will become more accurate. But you want to strike a balance between having to do many experiments and the accuracy. If your accuracy is already good enough, then you can stop fabricating these samples. And the distribution of the data is also very important. So if you only fabricate samples that is only in this part, it's very difficult for the model to predict in the other region. Yeah. So thank you for the nice question.
Okay, thank you, Mr. Okay, so who want to ask some question? Maybe it's about the NAIST.
Yeah, about nice or research.
Coming? Okay. Okay.
Okay.
Thank you for the opportunity. My name is Syarifani Yahya. I'm a master student. From my bachelor's, I have thesis about plasma.
Okay.
And you mentioned before there is plasma from argon. I wanna ask about how you make the plasma argon.
Okay, that's a good question.
Yes, thank you.
So I didn't explain here, but okay, maybe it's too far. But in this plasma, we used an ICP, inductively coupled plasma. So it's a special type of way of generating the plasma. So it's very dense in a large area. So usually this ICP plasma is used for etching. So ICP RIE. So reactive ion etching. So we use that equipment to generate the plasma. But we didn't introduce, like for example, etching gases like CF4. So if you introduce CF4 gas and not only argon, what will happen is that the high energy ions or high energy the CF4 will also interact with your material and it will sputter or etch. So we did the plasma treatment without the CF4, so only argon. And it's not only limited to ICP, you can also use atmospheric plasma. So I didn't show here, but we also successfully used atmospheric plasma system in order to functionalize or make oxygen vacancies in the semiconductor film. So thank you for the nice question.
Is it enough, Miss? You wanna ask again? Something? No?
It's fine.
For ICP method, did you use vacuum system or not? Vacuum system.
It's not vacuum. So it's not the very high vacuum, so not 10 to the minus 5, so it's only 10 to the minus 3. Yes.
But pure argon inside but pure argon, just argon.
Yes, just argon. So what you do is you vacuum first. This is because if it's in atmosphere, you will have oxygen, nitrogen, and other particles. It will collide with your high energy particles, right? So it will not be as effective. But as I said, it can also be done using atmospheric plasma. Yeah.
Thank you.
Thank you.
Okay, ladies and gentlemen, give applause for this question. And then who wants to ask a question again before? Okay.
Okay, good morning,
morning.
Dr. Juan. Thank you for the presentation. And my name is Syahrul Ramadhani. I am a Bachelor of Physics, and my thesis is about using DFT for calculating the spin texture of material. And you cite that you using machine learning than using DFT, and I was just wondering about what is the main limit of the DFT compared to the machine learning that DFT cannot calculate the ultra wideband for amorphous materials. Is it because DFT cannot calculate some parameter at once or something else? Thank you.
Thank you. So that's a good question. So DFT is also good, but it's limited in some applications like amorphous. So in amorphous materials, you cannot accurately predict it using DFT because in DFT, you construct a crystalline cell, right? And then if you want to make an amorphous, you heat it at a very high temperature and then you quench it. And then you have a random orientation. So at some point it fails there, and at some points it's very difficult for DFT to accurately predict, especially the band gap. Yeah, so it's well known that predicting band gap or Fermi level using DFT for amorphous materials is quite difficult. For crystalline materials, it's no problem. Yeah, except for the band gap part, I think. Yeah, thank you.
Okay, thank you very much.
Okay, thank you. Who one can? Okay.
Thank you very much for your sharing. I'm interested about the sensor one, and I want to ask about the analytics that the sensor
This one?
input. Yeah, the sensor.
Unfortunately, I don't really do sensors, but what is your question?
I'm interested about the analytics of the sensor and how the output of the sensor, like that. So.
Analyte. So yeah, I don't really work on sensors. So I'm just showing that it can be applied on sensors. But for example, for amorphous IGZO, so this material is very sensitive to light. So especially UV light. So what happens is that if you expose the amorphous oxide semiconductor to UV light, the current will increase. So that is the way it senses light. So another way of using amorphous IGZO or oxide semiconductor as a sensor is for sensing moisture. So for example, or oxygen. So for example, what happens is that if the oxygen adsorbs on the surface of the amorphous IGZO, it will capture the electron. And what will happen is that the characteristics will shift positively. So in that way, you can use the threshold voltage in order to sense the presence or absence of oxygen. Or in the moisture's case, it will shift negatively because it will increase the electrons. Yeah, so that's how we use it as a sensor. Yeah.
Thank you very much, sir.
Yeah, I'm sorry, I'm not really doing sensor research.
Okay. Any question? Okay.
Okay, big thanks for the opportunity. Thanks for the presentation in advance. My name is Jurnansha. I'm from master student in this department. My question is, regarding graphene materials. As you crystal clear mentioned before, you don't use graphene material because it's pretty expensive in your experiments.
Expensive.
Yeah, it's expensive, and you mentioned that indium zinc oxide, I mean, could be changed by other materials. And then one of the materials is ultra wide bandgap materials. All right. And based on my experiments, I got bandgap semiconductor materials because I work with graphene materials, especially RGO. So my question,
IGO.
RGO.
Indium gallium oxide.
No, RGO, reduced graphene oxide.
Induced graphene oxide. But the band gap of that is it's not wide band gap. So it's maybe less than 1. Right? Yeah.
Yeah, because I got around 2.5 electron volt.
Oh, really?
So yeah, so is it possible to change the indium zinc oxide by using RGO that I get based on my experience? Thank you.
I'm not familiar. I'm sorry. Maybe it's possible because graphene oxide is just carbon, right? So carbon will definitely interact with the oxide semiconductor. So I think it will change the property. Yes. But I don't know which way it will go. So actually in our field, we don't like carbon that much. We want to remove carbon as much as possible. Yeah. Because the way that carbon interacts with the oxide semiconductor is not well understood. Yeah. But maybe you can try. Yes.
Okay, so it means HGO would be able to be applied or not based on Fermi level. I mean,
maybe you can change the Fermi level.
yeah, to be more conductive, as you mentioned by your
Yes,
Fermi level
maybe,
methods.
Maybe, yeah. But I have no experience with it, so I can't give the accurate answer. Yeah.
Okay.
But it's an interesting way to functionalize. I know people are using reduced graphene oxide, right?
Yes.
Reduced graphene oxide in solar cell applications in order to functionalize the electrode. Or for example, I'm not sure if it's the HTL or ETL, but I'm not part of that field. So some of my colleagues are doing that type of research. Yeah.
Okay, full of thanks.
Okay, thank you. That's your first question. Anyone who want a question? Have a question? Maybe Pak Ahmad?
Maybe just comments.
Yeah,
thank you, Bermuda Sensei, for the presentation. And I think it is very interesting because it remember me about my final project in Bachelor. Yeah, in Bachelor, I did fabrication of thin film transistor, and our dean actually he also expert in organic semiconductor, actually in TFT. But later on, the problem is the equipment. That's why I want to know what kind of equipment do you use in this experiment? Actually, we have spin coater, we have mini CVD, and also we need the low temperature. Do you have any suggestion for us? What can we do with?
Yes, so that's a very good question.
And the second question is about the use of the machine learning. Yeah. Now my research is about fabrication of nanofiber, fabrication of nanomaterial, and yeah, it is very difficult to find the best properties if we have to do many experiments.
Yes.
Yeah, many, we need more money, we need more time and anything. And I think the machine learning is a breakthrough, I think. Yeah,
Yes.
it is, and I hope with your presentation we can discuss more about the method that you use in machine learning for fabrication. Yeah. We fabricate nanoparticles, we fabricate nanofiber, we fabricate also the semiconductor materials, and the problem is and actually it is the first presentation about machine learning determining the band gap, I think, in our department. So I think it's very interesting. Yes, thank you.
So thank you. Thank you.
To the future, we
You
No,
still
no.
need because
because we need
we need to do experiments as
yeah,
but not as many.
we did machine learning for sensor. We need about at least 100 data. Yeah.
Yeah,
So so for the experiment, I think maybe if you said about 50 or 30,
Yeah,
yeah, I think it's good enough.
Yeah.
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 Okay, thank you.
So yeah, that's a good, very good comment. Yeah. So as for the equipment, you asked about the equipment we used. So in my group, we only use spin coater, hot plate, UV ozone, and annealing equipment. So it can be an oven or any annealing equipment. Clean room, unfortunately. Yes. But I think you can also do that in a semi-clean room. If you just require students to wear clean wear, yeah, and clean it every week. Ah, that's a good question. So humidity is actually a killer of solution process devices. If you have, unfortunately, if the humidity is too high, you need a glove box. Yeah, but it's still possible even if the humidity is high, but the performance will be poorer. But I'm oversimplifying that because some materials react well with humidity. Some materials don't like humidity. So it depends on the layer that you're trying to form. Yeah, thank you.
Okay, thank you. And the last question? Okay. Last question?
Okay, thank you, Bermundo Sensei, for the nice presentation. So I have actually one more general questions.
Yeah.
I mean, more industrially focused
Yeah.
topic, since you presented about the possibility for this fabrication in the large scale compared to the what is it, the vacuum system things, which normally the semiconductor industry use. So that's actually my question is actually about the how welcome is the industry to this kind of wet chemistry process, since as my experience when I was doing my postdoc and we were collaborating with Zeiss, a German company, the optics, and from the interaction with them very intensively, that they actually not really the big fan of
Yes, I know.
of wet chemistry process. So since at the moment, as I said, that most of the process is still in the vacuum system. So yeah, I'm just wondering about this, how welcome they are. And the next question is about the a bit technical, since you also use the what is it, the excimer laser for changing the conductivity of the gates. And my question is that as I know that when you irradiate with this such a pulse laser, that you only get the effect on the surface area. And I mean, is that enough for changing all of these layers that you need, or maybe you have to find the optimum parameters, right, to what is it, to change all the regions into crystalline, I mean, in the crystalline phase.
Unfortunately, I don't have the slide here, but
Ah,
very
okay,
good
yeah.
question. So
Yes.
the first question is the receptivity of the companies, right?
Yes.
So yeah, it's a challenge for most companies to use wet process. This is because the performance is not the problem right now. The stability and uniformity is the problem. But actually, we're working on several industry collaborators, like companies that are interested in this topic. So we're also fabricating solution processed films for them to be used for their transistors. So there's already like a start of the collaboration between industry and the university level in terms of solution processing. And for the second question, unfortunately, I don't have the slide here, but the question is very good. So you're asking if it's only at the surface, right? The laser. So the important part of the laser radiation is the wavelength and the extinction coefficient of the material. So depending on the extinction coefficient of the material, it will dictate how deep the laser will interact with the material. So this is aside from the wavelength. So the wavelength also controls how it will interact with the material. So in this case, we calculated the penetration depth of the laser to the material. So we found that the laser will interact with the material up to 50 nanometer using the krypton fluoride laser. And we deposit films, or no, up to 70 nanometers. That's why we deposited films with thickness of around 70 nanometers. So this means that the laser will interact up to 70 nanometers, or the whole film. Yes. But that's a great question, yeah. Thank you.
Check. Okay, thank you for the answer. So the last question. Okay.
I've introduced myself before.
Yes.
My name is Nabila. I want to ask you about, especially it's about scholarship in NAIST.
Okay.
Is there any offering scholarship from NAIST?
Yes.
Oh yeah.
Many scholarships.
Yeah, especially for a master program.
Yeah, even
that
master
we can
programs,
get.
we have.
Yeah. Can you please explain the requirement or the admission?
Unfortunately, I don't have the slides.
Yeah.
So, but you can join the NAIST DMS Study Abroad Fair on September 7th. So we have many scholarships, like the MEXT scholarship by Embassy, MEXT scholarship from NAIST, and the NAIST International Scholarship. So, of course, the slots are limited, like up to 9, I think. So it's competitive, but I think just try. Yes. I think both, I'm not sure yet, but I think both masters and PhD, yeah. Yeah, but the internship is for PhD. Masters, yes. Hmm. Yes. So you can enter NICE, yeah, masters. So right now I have a master's student also from Indonesia, from Hasanuddin University. Yeah.
Thank you.
Thank you.
Okay, thank you for that question, and give applause for us. Okay, and the time is back to the moderator, please.
Okay, thank you very much for Bermundi Sensei for the nice presentations. And we very thank you for your coming in physics departments, and I hope the students have a new insight for about the research experiments. Okay, I will give to Mbak Mayumi for the next agenda.
Okay, thank you, Miss. The next agenda is to give some souvenir for Dr. Juan Paulo. So please welcome Mr. Eddie to give some souvenir and close this closing remark. Okay, we can take
Yeah. On behalf of Department of Physics, I would like to say thank you very much for your coming in our department and for very nice talk. Even I'm not so familiar because my topic is about magnetism, but from discussion maybe it's very interesting. And I believe that 2 or 3 participants, they will study in NAIST for next year, maybe for PhD. I hope, yeah. Yeah, yeah. And yeah, we have yeah, very small souvenir. Yeah.
Okay, come to, we will take a photo together. Oh, ditutup dulu, Pak. Close. Oh ya sudah. Oke, iya. Okay, okay. Thank you for ladies and gentlemen to coming to this session. And wassalamualaikum warahmatullahi wabarakatuh. And see you again. Yeah. So please come to forward to take a picture together.